Hi, I'm Yogesh Kumar. Let's discuss the FEA analysis process using SOLIDWORKS Simulation. The process of analyzing designs consists of the same basic steps, regardless of the type of analysis or model, although all of the following steps must be completed. Many of them can be done in any order desired by the user. First, a study is created. Multiple studies can be created for a single model if needed. A material is applied to the model, which contains the physical information such as the yield strength of the model. Fixtures are applied to the model, which represents the way the physical product is held. Loads are applied to the model to represent the forces that caused the part to deform. A mesh breaks down the model into a collection of small, simple elements. This allows the solver to find values such as the stress and displacement at each point where the elements join together. Once all of the previous steps are complete, the study can be run to calculate the results. Finally, the results are displayed in graphical plots according to the result type such as stress or displacement. In this lesson, I'll fix the 2 bolt holes of this bracket in place and apply a 500 Newton force on each counter board face. Using simulation tools, I'll find points with the highest stress along with the maximum displacement for the part. The bracket shown here will be used to run the simulation study, which will give us the stresses and displacements that result from the forces and fixtures applied to it. The fixtures will be added to the inner cylindrical faces of the 2 bolt holes, simulating the bracket being fixed in place using 2 bolts. Once the fixtures are applied, an external force of 500 newtons will be applied normal to each counter board face of the vertical wall. To begin creating the simulation study, I'll simply activate the simulation add-in. To do this, click on the drop-down arrow next to the options icon and select add-ins. And when the dialog box appears, check the box next to SOLIDWORKS Simulation as well as the Startup checkbox, if desired. Then click the OK button. Now I'll activate the simulation to begin a simulation study for this model. Select New Study. The Property Manager prompts me to create a new study, which I will name Stress Analysis. I'll make sure it's set to be a static study type since load does not vary with time, and material are linear material. Upon clicking the green check, the study is created. You can see here that the new simulation study has a number of items to be specified in order to solve them. These items can be defined step by step, or they can be done in any order, providing you the flexibility to define them as you want. There is no specific workflow for the simulation tree. However, some of these items must be completed for the solver to run, to begin the finding aspects of the simulation. I need to access the simulation tools. This can be done by right-clicking on any of the items in the simulation, or by enabling any of the tools from the simulation command manager. A common first step in a simulation is setting the material for the part. As mentioned before, this does not have to be the first step. I'll right-click on part, and then select Apply Edit Material. Here, if a material had already been defined for the part in the design process, that material would be pulled into the simulation study, automatically eliminating this step. However, a simulation study adds flexibility by allowing you to select any material for this study without changing the material defined in the 3D CAD model. You have access to a rich material library for your simulations. For this study, I'll select the material alloy steel. And you can see below that some of the material properties are shown in red and blue. The red properties are required in order to run the static simulation and the blue properties are optional. One of these properties, the material's yield strength, is one of the most important properties which will come up later when I review the results. With the material selected, I'll click Apply and close the dialog. Now you can see the material applied to the part shown in parentheses in the tree, including a green check shown on the part icon, which indicates that this study item is complete for this model. There are no connections needed since this is a single part and there are no part-to-part interactions present in the model. Now that the material is defined for the simulation study, I can begin to finding fixtures in the model. Fixtures define ground interactions, which defines paths that are not explicitly modeled in this simulation study. As mentioned earlier, the fixtures will be applied to the 2 bolt holes in the base of the bracket. This time, instead of accessing the simulation tools from the tree, I'll go ahead and click on the drop-down arrow underneath Fixtures Advice and select the option Fixed Geometry. This brings up the Fixture Property Manager. I'll make sure that the Fixed Geometry option is selected as the fixture type, and you can see a graphic visualizing how the rest of the part moves relative to the fixed face. To fix the interface of the cylinder, I can click on it, as well as the interface on the other side. And if I zoom into the hole I just selected, You can see green arrows pointing in all directions. Fixed faces appear with green arrows in the graphics area. And the number of arrows indicates how many directions are fixed. Now I'll click the green check to complete adding fixtures in. You can see the fixture added in the simulation. The next step is to add the external load to the model. You can see a number of loads that can be applied to the model, including some prescribed displacement as well. For this study, I'll choose the option Force. The Force Torque Property Manager appears. I'll select the force as my type. I'll apply the force to the face of the counter bore. I'll make sure this is a normal force and set it to 500 newtons on each face. Notice that the arrows in the graphics area are shown in purple, which indicates a force. They are also pointing in the direction of the force, which is normal to the face. Now I'll click the green check to finish adding the force. The simulation tree updates, and the force is listed under External. The process of meshing takes model geometry and turns it into a collection of small, simple shapes that the software can use to calculate the stresses and strains. Each of these small, simple shapes is referred to as an element. And the combination of all of the elements is known as the mesh. To apply the mesh to the model, I'll right-click on Mesh, and then select Create Mesh from the menu. The mesh density can be adjusted here with a sliding scale ranging from coarse to defined. If the density is set to coarse, there will be less elements created in the mesh, which often allows the simulation to process quicker, but is less accurate. However, if the mesh is set defined, more elements are generated in the model, which allows the simulation to produce much more accurate results. However, it takes much longer to solve the study. I'll go ahead and reset the slider by clicking the Reset button, which places it in the center of the scale under the mesh parameters. There are also 3 meshing algorithms that can be used: Standard, Curvature-based and Blended Curvature-based mesh, which calculate the mesh for the model. For this example, I'll select Curvature-based mesh, which creates a mesh with variable element size. This allows for a more accurate resolution of small features in the geometry. Now, when I click the green check, you can see the mesh applied for the entire model, which has broken the model down into a collection of elements. Now that all of the necessary setup information is complete for this model, I can go ahead and run the study. I'll click the Run this study button in the command manager and the solver runs. Once the solver is complete, a results folder appears in the simulation tree listing various results. First, I'll double-click on the plot, Stress 1, which is also known as the von Mises stress. A color gradient appears overlaid on the model, which corresponds to the key shown to the right. Each color indicates the stress found at that point. Stress is the internal resistance of the part to the loads applied to it. If I take a closer look, I can see that stress concentrations developed at the holes of the bottom plate indicated by the yellow and red coloration. The bolt holes also indicate regions of high stress. And the key on the right. Notice the red arrow pointing to the yield strength. The yield strength is the highest stress the part can withstand before the part can return back to its original shape. If any region in the model exceeds stress value, then this is permanently deformed. This means that the regions in the model that are in the color pointed by the arrow will get permanently deformed and will not return back to their original shape, which can often be considered a mechanical failure. Now I'll take a look at the displacement. This plot shows how far the part moves from its original shape. However, the deformed shape shown in the graphics area is not a realistic representation of the part. After the load is applied, this displacement plot is exaggerated by a scaled amount as indicated in the top left corner. The displacement of the part can be animated by right-clicking on the plot in the tree and then selecting. This shows how the part moves when experiencing the external load, which is also exaggerated by the deformation scale. In reality, the maximum displacement for the part is 0.09 mm, which is much smaller than what is being shown graphically. This completes the entire simulation study, including showing both the stress plots and the displacement plots for the model.